Hello, we are looking at the online ads demo running on top of the DataTorrent streaming platform. In this application, we have impression and click events coming in. We pay money for each impression and make money for each click. These events have different dimensions of what ad size, from which publisher, inventory sources, and for what advertiser. For each combination of these dimensions, we will process and aggregate the number of impressions, clicks, total cost, and total revenue for each minute, hour, and day. We then write these in real time to a Redis in-memory store for ad hoc querying of our real-time data. Next, we're going to look at the application in the IDE. In the IDE, we define the operators that we have seen on the slide and connect them through streams. In addition, we see attributes. This application is a partitioned application, so we will have partition attributes set, and we will further explain this when we look at the console. In the code, you see the four operators: ads, item dimension, input dimension, bucket, and Redis. Next, we're going to look at the console. The application is running. The first thing we notice is there are many more operators than what was defined in the logical DAG. The reason for that is that the application is partitioned. We find 8 partitions and in total 28 operators in 10 containers. The incoming impressions and clicks are around 1.4 million events per second, and the total computation of the DAG is around 12 million events per second. There are 28 operators over the 10 containers, and as mentioned, the operators are partitioned. What we see here is 8 operators of input, 8 instances of input dimension, and 8 instances of bucket, while the Redis operator is a single instance with a unifier. To explain the concept of parallel partitioning, let's sort by node. What we see here is that there are 3 operators on the same container, 5 for example, which is on node 10. These 3 instances belong to one parallel partition, and we have 8 of those. In this DAG, we are computing 3 dimensions. What we see is that an input of approximately 1.4 million aggregate results in an 8x output from the dimension operators. Again, these are 3 dimensions. For each event, there are 8 events generated. It is important to note that this application is scalable. It scales horizontally. It would be possible to handle 10 or more dimensions. The aggregation in this DAG happens in the bucket operator. As explained previously, 3 operators form a partition within one container. The last operator is bucket. Bucket will aggregate data. That means it will take in many more events than it emits. The final operator is the Redis operator, which writes to the Redis data store. Let us go to the dashboard to see real-time charting of these metrics, refreshing every 5 seconds. You see here live charts for cost, revenue, clicks, impressions, click-through rate, and margin across all publishers, advertisers, and ad sizes. We can also query for specific advertiser-publisher ad size combination and see the live charts. Let's try this. See all the data for this combination, and we see how the charts are updating dynamically. The implication of this is that we can monitor and set alerts on undesirable behaviors. For example, alert me when there are conditions where I have margins of less than 5% or when the CTR is less than 0.1%. Then we can take immediate action of this real-time data by not buying low-performing inventory or by buying more of high margin inventory. This concludes this demo, and it highlights the ability of the DataTorrent platform to horizontally scale and handle massive amounts of dimensional data.